The space between galaxies is not empty. That sentence contradicts almost every intuition we carry about the universe, and the evidence behind it has quietly reshaped how astronomers understand the largest structures in existence. Our nearest large galactic neighbor, the Andromeda Galaxy, sits roughly 2.5 million light-years away. That number is so large, it resists comprehension, so consider it this way. Light, traveling at nearly 300,000 kilometers every second, takes 2.5 million years to cross that distance. The light arriving in your eye from Andromeda tonight left its source before our own genus, Homo, existed on Earth. And yet, between the Milky Way and Andromeda, that gulf is not a clean vacuum. It is threaded, filled, and structured in ways that only became clear once instruments sensitive enough to detect near nothing were pointed at it. For most of observational history, the space between galaxies was treated as absence, a backdrop against which galaxies were pinned like objects on a board. The expectation was reasonable. Matter, after all, clumps under gravity. Stars form galaxies, galaxies cluster. And between those clusters, logic suggested, there should be very little of anything. What observations have revealed instead is a vast, diffuse web of gas, dust, stray stars, and gravitational influence that occupies what we once called the void. The leading framework for understanding this structure is called the cosmic web, and the Milky Way and Andromeda are both embedded in one of its filaments. The cosmic web is a model of large-scale structure supported by multiple independent lines of observation. Surveys of galaxy positions across the sky, particularly the Sloan Digital Sky Survey, which mapped hundreds of millions of galaxies over more than 2 decades, revealed that galaxies are not distributed randomly. They trace sheets and filaments that intersect at dense nodes, with vast underdense regions called voids between them. The filaments connecting galaxy clusters are not merely geometric, they contain matter. Specifically, they contain warm-hot intergalactic medium, a diffuse plasma of ionized gas at temperatures ranging from roughly 100,000 to 10 million Kelvin. Detecting this gas is extraordinarily difficult. Because it is so diffuse and so hot, it emits and absorbs primarily in the far ultraviolet and soft X-ray portions of the spectrum, wavelengths that Earth's atmosphere blocks entirely. Observations from space-based missions, including the Chandra X-ray Observatory and the XMM-Newton telescope, have detected signatures consistent with this warm-hot intergalactic medium along sight lines between known galaxy clusters. These detections carry real uncertainty. The signal is faint, the background is complex, and disentangling the intergalactic contribution from foreground and background sources requires careful modeling. Researchers note that some detections remain contested, and the total mass budget of this diffuse gas is not yet precisely constrained. What is well supported is why this matters cosmologically. Models of structure formation predict that a significant fraction of all ordinary matter, sometimes called baryonic matter, to distinguish it from dark matter and dark energy, should reside in these filaments as warm, hot gas. For years, observations of galaxies and galaxy clusters accounted for only a fraction of the baryonic matter that theory predicted should exist. The rest was called the missing baryons. The warm, hot intergalactic medium in cosmic web filaments is the leading explanation for where that matter went, supported by accumulating but not yet complete observational evidence. Between the Milky Way and Andromeda specifically, the intergalactic medium is expected to be even more tenuous than in denser filament regions. The local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and roughly 50 smaller companions, sits in a relatively modest filament. The gas within the local group's environment has been studied partly through observations of high-velocity clouds, clumps of neutral hydrogen gas detected by radio telescopes that do not follow the rotation of the Milky Way's disk. Some of these clouds are understood to be material accreting onto or circulating within the local group, though the distances and origins of individual clouds carry significant uncertainty. Beyond gas, there is another component to the intergalactic space that is even harder to observe directly: dark matter. The cosmic web's filaments are understood, within the standard cosmological model, to be primarily dark matter scaffolding, with ordinary matter tracing those invisible structures. Dark matter has not been directly detected in any laboratory, but its gravitational influence on galaxy rotation, gravitational lensing of background light, and the large-scale distribution of galaxies all point consistently to its existence. The filament between the Milky Way and Andromeda is expected to contain a dark matter bridge, though imaging that bridge directly, separating its weak lensing signal from noise, remains at the frontier of current capability. There is also the matter of stray stars. Not all stars belong to galaxies. A population of intergalactic stars, sometimes called intragroup or intracluster stars depending on the scale, has been detected in galaxy clusters and groups through the diffuse stellar light they collectively produce. In the local group, some stars are understood to have been stripped from dwarf galaxies through tidal interactions. These stars wander between galaxies, unbound to any single system, tracing the gravitational history of the group. They are incredibly sparse by any human standard, but they are there, and they represent direct observational evidence that the space between galaxies is not simply empty. The central question of what future observations could confirm or revise comes down primarily to the missing baryons problem. Upcoming missions and instruments, including more sensitive X-ray telescopes and next-generation radio arrays, are expected to map the warm-hot intergalactic medium with substantially better resolution and sensitivity than is currently available. If those observations confirm the predicted mass and distribution of filament gas at the level theory requires, it would resolve one of the outstanding accounting problems in cosmology. If the observations reveal less gas than predicted, or gas distributed differently, it would require revisions to models of how structure formed and how matter was distributed across cosmic time. The gravitational relationship between the Milky Way and Andromeda adds a consequential dimension to all of this. The two galaxies are approaching each other. Measurements of Andromeda's motion, using the Hubble Space Telescope's precise tracking of stellar positions over multiple years, established that the collision is not just probable, but essentially certain on a cosmological timescale, roughly 4 billion years from now. The intergalactic medium between them, the gas threads, the dark matter filament, the wandering stars, all of it is part of the gravitational system drawing these two structures together. The space between is not passive. It is the medium through which two of the largest objects in our cosmic neighborhood are already in slow, inevitable conversation. What the evidence changes is the concept of emptiness itself. The intuition that space between things is simply nothing served well when our instruments could not detect the diffuse, the hot, and the dark. Every improvement in sensitivity has revealed more structure in what was previously called void. Gas, at temperatures too extreme for optical telescopes. Matter spread too thin for early surveys. Gravity acting on things we have not yet directly imaged. The gap between us and Andromeda is 2.5 million light-years of something. Structured, dynamic, and still only partially mapped. The next question that naturally follows is what happens when that gap closes? When two galaxies, their halos, their gas, and their dark matter filaments finally merge. That process is already underway, measured in the slow drift of starlight across centuries of careful observation.